Hey everybody, welcome back. So we're doing part two today here. We're going to take a little bit more look into what those pesky electrons are doing as they're buzzing around the nucleus. Not just hanging out in energy levels orbiting like our friend Bohr thought. A little bit more in depth about that, not too crazy, but then I'm going to teach you a strategy for how we can kind of draw some of these patterns, because it's the arrangement of these electrons, kind of where they are and what they're doing, that allows us to start to do some predictions in terms of chemistry. It's based upon this kind of stuff. So again, taking a look at this, we're looking at valence electrons today, and kind of where electrons are hanging around in the electron cloud. So with this, hit the wrong button there. We now know that electrons, unlike what Bohr was hoping, don't just buzz around in nice little neat circles. He actually did a whole bunch of math back in his day, like I said, right around 1910, 1915, to actually predict exactly what colors of light electrons were going to be able to give off if they were jumping from energy level 1 to 2 and energy level 2 to 3 and back and all that kind of stuff. And it worked great. He had a fantastic, equation that worked perfectly for hydrogen. He could predict exactly what colors it was going to give off. And then he, plugged in the 2-electron system for helium. It's like, ooh, close. Almost there, right? So just a little tweak in the system. And then he tried to do any of the higher level ones, and it didn't work. He thought he could predict it. He thought it was as simple as these easy circular energy levels with electrons just following each other nice and smoothly around in these little orbits like planets, are orbiting the sun. And now we know, based on the works of people that started about 20 years later and through the last 100 years, that electrons are crazy little buggers. They fly around all over the place. They act like solids. They act like waves. They move almost the speed of light. They're all over the place. They do all kinds of crazy stuff. So a better way for you to picture what an electron doing is to picture more like bugs in a cloud. And I put these two kind of pictures up there. Imagine if you talking about any one of these little gnats that's in here. You could follow one of those little gnats around, or you could follow one of these big butterflies around. But if you look at it from a distance, it kind of looks like a cloud. And if you look at it really close, you can see the individual sort of moving around. But not a single one of these is following a real simple path. They have energy to them. You could imagine a different, a bee kind of flowing through, you're kind of slow doing something different, or a real fast little bug going, real different in there. Electrons are kind of like that, where they're flying around one another. They're sort of not quite chaotically interacting. They're interacting in a somewhat predictable way, but it's certainly not as easy as things moving around in a circle. So sorry, but that's just one of the things that we know. And as we do this now, these people that came later, these were the guys that were starting to use this quantum mechanics. If you start to hear kind of when they're throwing that quantum behavior in there, this is what we're starting to talk about, is that these modern models are starting to treat electrons more like the weirdness that they actually are. And electrons, it's really good to think about them as sort of being like halfway between matter and halfway between light. They definitely have behaviors of both in a way that's really interesting. And again, Erwin Schrödinger was one of the guys that actually studied this. If you want to look up some interesting stories, read about Schrödinger's cat. And it's a parable. It's just a fable that's told to kind of try to get a story, an easy to understand story that gives you some ideas about how weird electrons actually behave. So one of the things that we knew right away from dealing with Bohr's model, and Bohr even tried to do this himself, is that he knew that energy levels weren't single energy levels. He knew that pretty quickly, even as he started working with helium and lithium, the relatively small atoms. So he came up with the idea, instead of energy levels, maybe there's sub-energy levels. So he said that energy level 1 had 2 sub-levels to it. Energy level 1 had 1 level to it. Energy level 2 had 2 sub-levels to it. Energy 3 had 3 sub-levels to it. Energy 4, 4 sub-levels, and so on and so forth. It ends up looking like a record after a while, where there's just all these little grooves for all these little energy levels. And even that wasn't enough. We now know that these sublevels are broken down even further into things called orbitals, and that orbitals are broken down even further yet. So the more we know about the atom, in a sense, the less we know about it. And it's because these electrons are acting so crazy. So what we do now is we instead talk about kind of the holistic behavior about it and think about it in terms of the electron cloud. I know that that's a model that you understand and that you've heard before. This is not a new idea. But here would be like what energy levels would look like within an electron cloud, right? The whole thing is kind of a fuzzy mess. But even within there, there's sort of some organization within chaos. So this sort of idea of that electron cloud is useful for us in truly understanding the crazy behavior of atoms. And as you get into higher levels of chemistry, this quantum nature gets more and more important. For right now, though, if we still draw this more like a Bohr diagram where we draw energy level, if I can get my pen, I do that every time, don't I? Where we do, here's energy level 1, and then here's energy level 2, and then here's energy level number 3. Ugh, well, that's supposed to be round, but here's energy level number 3 going around out there. We can still kind of simplify this crazy cloud in something that still looks a lot like a Bohr model. So we do still use the Bohr model to help us draw some very oversimplified models, but these do still have some predictive value to us. So here's an idea or a simplified version of a Bohr model. Now, in our Google Meet session, we're going to practice drawing these. But one of the things that you need to realize, again, these are not simple orbits. These are these cloudy sorts of shells, but there are still some rules within here. One of the things is that, number one, you got to know how many electrons there are. So back to the beginning of the year, remember that the atomic number of an element gives you the base number of electrons as well. It's by definition the number of protons, but you can also use it to start off with the number of electrons that are in an atom. Second thing is your general rules are kind of written over here, is that the first shell is a real small shell. It can only hold 2 electrons at the most. That's as much as it can hold. And the second shell is a bit bigger. It can hold up to 8 electrons. And there's reasons why that magic number is 8, but it can hold 8. That's all you really care about right now. The third shell can hold quite a bit more, the third, fourth, fifth shell. And there's a little formula for figuring out what it is. N here means the number of the shell itself. So if I want to talk about the third shell, I would do 2 times the third shell squared, or 2 times the fourth shell squared. 2n squared would give you the maximum. So there's actually 18 that could fit in there. However, the good news for you guys is that if we're talking about the outside shell of any atom, any Bohr model atom that we deal with, the outside shell will have a maximum of 8 electrons. So our magic number really is 8. And again, you don't want to know why, take Chem 2, we'll talk about why. But in terms of this one, when we're drawing these things, our Bohr diagrams can still be useful to us, knowing the first level's 2, the second level's 8. And for the purposes of what we are going to do, the third level is essentially going to have 8. This highest energy level shell, the outside shell, whichever one it is in an atom, we give it a name and we call it the valence shell. So the first shell could be the valence shell in hydrogen and helium. The second shell could be the valence shell in the second row of the periodic table. And then the third shell could be the valence shell. Whatever the highest one is, could be the fourth or the fifth or the sixth. But whatever that outside one, we call that the valence shell. Now, why do we care about this? Well, it turns out those valence shell electrons are actually really important to us. And it's these outside energy levels, these outside electrons, are the ones that are really important in determining chemical bonds. We're going to come back and do a lot more with this, but I wanted to give you some context for why are we focused on all these damn electrons and why are we drawing all these dots? Because it's these dots, these valence electrons, the highest shell electrons, that magic number of up to 8, right? That is going to determine how things bond together. And it tells us why sodium is NaCl and not some other formula. And why is water H2O and not some other formula? Why is ammonia NH3 and not some other formula? And it relates to valence electrons. So in order to be able to do this, rather than drawing Bohr diagrams all the time with circles and circles and circles, these bullseye kind of models, I'm going to teach you a shortcut. And this shortcut is called Lewis diagrams. You may have already done this in middle school. It kind of depends on who your teacher was. But these Lewis diagrams are a real shortcut way of drawing Bohr models, kind of really reducing it down. And it's going to be a way for us to kind of figure out how many electrons are in this valence shell. So your skill is that we're going to practice is going to be drawing Bohr models, this style of Bohr models. I'll call these mini Bohr models. They almost look like, a little half of an arc here. We're going to be drawing those, and then we're going to be drawing Lewis dot elements for elements 1 through 20. So it's not as bad as it sounds, I promise, and there's some patterns to it. So the rules for drawing Lewis diagrams, the good news is, we only draw the valence electrons. So if you take a look at oxygen here, this is a little Bohr diagram for oxygen. We could have a total of 8 electrons to it. It starts with 8 protons and 8 electrons. So it could have 2 electrons in the first energy level, and the remainder go in the second energy level. That's why there's 6 out there. So when we draw our Lewis structure, all we need to draw is the symbol of the element, O for oxygen, and we draw our 6 dots around the outside. Now I'm going to have you guys be maybe a little more sophisticated than middle school. So what I want you to do is draw your dots at the corners. Here's what I mean by corners. If we have an element X, the corners are the top, bottom, left, and right. These are the corners that I'm referring to. So here, 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 and here. So if I'm going to draw oxygen with 6 dots to it, I would draw my symbol oxygen, and I want to draw my 6 dots. So I go 1, 2, 3, 4. Notice how I filled the corners up. And then I'm going to start pairing them up, 5 and 6. Or you could do like this one, 5 and 6, where the bottom 2 is filled up. And that's totally fine. But that's how we're going to start drawing these to pair them up. We're drawing fluorine, for example. Fluorine's got a total of 9 electrons. 9 protons means 9 electrons to start, 2 in the first energy level, and then the 7 remaining ones go in the second energy level. And you can see here's the Lewis structure for fluorine. Our symbol goes in the middle, and then we've got our 7 valence electrons around it. So 1, 2, 3, and 4, and then 5, and then 6, and then 7. So I've only paired up some of them, and then there's one that doesn't have a partner to it. If I'm going to draw sodium to it, sodium actually has a total of 11 electrons to it, so 2 in the first energy level. Then there's 8 would go in the second energy level, and then there's one last one all by itself in the third energy level all by itself, and so that's why sodium Na only has a single dot to it. We're going to practice this particular skill a lot in our meeting. This is what I really need you to be able to do, is to draw Bohr model diagrams and to draw Lewis dot diagrams from them. So drawing Lewis structures or Lewis diagrams for elements. So as we get going with this, what's nice is that we can then use this to predict some really important things about bonding. So one of the things that we know now about electrons and behavior is that either having a full shell or an empty shell is particularly stable. This is what atoms sort of want to do. So this means that they will gain or lose electrons in order to be stable. And when atoms gain or lose electrons, that's how they become ions, and they can either be cations or anions. So again, coming back around to some of these things that we did a long time ago. So our friend lithium here, for example, is going to take this one and give it away. Somebody else can take it, empty out. And if it empties out, it becomes a +1 ion because it's lost 1 electron. Or beryllium, when it gets rid of things, it gets rid of those 2. And now it's emptied out and it becomes a beryllium ion. I'm going to go down to these couple ones because we're going to practice this in our meet. The other ones down here, some of these guys want to fill up their shell. So like nitrogen right here, it really wants to have a full shell, and a full shell is 8. So if you take a look what nitrogen has right now, nitrogen wants to get 1, 2, 3 more electrons, which would make it a nitrogen ion. 3 more electrons gives you 3 more negative charges. Oxygen, we've been dealing with her all year long. Oxygen wants 8. It currently has 6. So it's going to do 1, 2 more and becomes oxygen 2-, or the oxide ion. And chlorine will fill up its 1 spot like that and become chlorine 1-. Argon, by the way, argon's already full, right? It's got 8. It wants 8. It's already full. It does not need to gain or lose anymore. And these guys, I don't know if you remember a long time ago, they're called noble gases. They don't form ions. They don't need to do that. They're already full. Lithium, which only has to gain or lose 1, in this case it's going to lose 1, that doesn't take a lot of energy to lose 1 electron. It's really an active metal. It's highly reactive, really wants to get rid of that electron. Chlorine, on the opposite, it really wants to gain that 1 electron to fill up that 1. It doesn't take a lot of work to do that, but it really, really, really wants to fill it up. And it's a really active type of a metal. Non-metal, on the other hand, we would call these guys halogens, and that's its whole family that does that. So again, we've seen these patterns before, these patterns of ion charges from the periodic table directly related to the Lewis dot structures and the formations of these ions. So when we come back in our next little bit, we're going to start using this in our next section and unit to start predicting types of bonding. This is ionic bonding and covalent bonding. And then as we get into next week, we're going to actually start building molecules doing this stuff and figuring out how to put these things together to create different types of compounds. So there you go. using the electron structure and the idea of energy levels and the electron cloud to be able to figure out some things like Lewis structures, how many valence electrons are out there, and to be able to figure out how many they could gain or lose to become an ion and then start to bond together and do some interesting things. All right, I will see you in the Zoom meets. Have a good one, you guys. Bye.